Welcome to Xiaol.x. Today, Muon, the spectral optimizer revolution. By reading the low stable rank geometry of weight matrices, spectral gradient descent steers learning.
A new optimizer called Muon is decisively beating the industry, standard atom, by fundamentally changing the geometric space of training. Instead of just tuning coefficients, Muon learns a linear transformation that reshapes curvature, leading to faster convergence.
There's a secret lurking in many neural networks, a single dominant direction in weight space, the so-called rank 1 spike. Standard optimizers wander aimlessly on the flat plateau around it. Spectral methods, however, see the spike for what it is and ride it straight to better solutions. In this episode, we visualize how that works.
For years, we've searched for the signal. Now we have it. A single layerwise condition, gradient nuclear rank greater than activation stable rank, tells us exactly when spectral updates beat Euclidean steps. It's simple, it's predictive, and it unlocks up to 72% more loss reduction in one move.
Welcome to the deep dive. So if you're out there training one of these, massive deep neural networks, the ones that just eat up thousands of GPU hours, the biggest bottleneck is always optimization. We're still relying pretty heavily on these first-order methods we've had for years, things like SGD or, its more sophisticated sibling Atom. And they're efficient per step, sure, but when your training run is measured in weeks, any speed up is it's precious. And that's why this new research into spectral gradient descent, and especially its momentum version, Muon, is just so compelling.
It really is. Muon has been seen to match or sometimes decisively beat Atom in large language model pre-training. And we're not talking about just tweaking a learning rate schedule here.
No.
These optimizers are fundamentally changing the geometric space that the network weights are updated in.
Exactly. So when you get a performance leap like that, at that scale, it demands a mathematical explanation.
Right, and that's the core mission for this deep dive. We want to answer that one question. Under what precise geometric conditions should these spectral updates actually outperform the standard Euclidean methods? It has to be geometry, but what geometry?
And the sources provide this surprisingly elegant and quantitative answer.
They do. It all boils down to comparing two specific layer-wise ratios. One comes from your feature maps, the other from your parameter gradients. And this analysis, it connects the success of Muon directly to this often overlooked degenerate structure of the learned representations inside the network.
Okay, let's unpack that geometric condition, because this really feels like the fundamental aha moment of the whole thing. We're basically comparing the progress you make with one standard gradient step versus the progress from one spectral step.
That's it. And when you boil down that comparison, you get this inequality based on two critical properties of each layer. We're not looking at the whole network at once. We're looking at each individual parameter block, say a weight matrix, and how it's interacting with the features coming in. So we need to measure two complementary things. Let's start with the feature side, the data coming into the layer. This is something called the stable rank of incoming activations, or SATF.
Stable rank, what does that actually measure?
Conceptually, it's measuring the effective dimension of your feature matrix. So if the stable rank is low, it means that even if your network layer is, say, thousands of neurons wide, the data is really only active and informative across a handful of key dimensions.
So even in a huge network, your features are kind of squashed or highly degenerate. All the information is focused into just a few dominant vectors.
Precisely. And that sounds like an ill-conditioned problem for a traditional optimizer, right?
Absolutely.
Because it is. Low stable rank implies strong degeneracy. So now we flip to the other side of the coin, the optimization effort. And for that, we measure the nuclear rank of the gradient, or NR of G.
Okay, so if stable rank measures how focused the features are,
then nuclear rank measures how spread out the optimization signals, the gradients are. A high nuclear rank means the gradient is pulling the optimization effort across many different dimensions, even the subtle, non-dominant ones.
And this is where it all clicks into place. The central condition, the thing that predicts when spectral descent wins, is just that the nuclear rank of the gradient has to be greater than or equal to the stable rank of the activations.
That's the inequality. NR of G is greater than or equal to state of A.
So spectral methods win if the optimization signal is really spread out relative to how degenerate the features are?
Exactly. And the implication is huge. If your feature degeneracy, state of A, is bounded by some small constant, say the number 2 or 3, and the gradient's nuclear rank NR of G scales up with the dimension of the network, then the advantage of the spectral optimizer also scales with dimension. The speed up is directly linked to how big your network is.
So the reason Muon works so well is that it's just geometrically adapted to the specific landscape that large neural networks create, this spectral imbalance.
That's the core takeaway. Now we just need to confirm two things. First, why is the stable rank, S of A, consistently so small? And second, how does the nuclear rank, SDAJG, manage to get so large?
All right, let's start with that denominator. The stable rank of the features. The sources kept calling this a structural property reflecting strong degeneracy. So why are our features so squashed?
It's largely a consequence of using non-centered activation functions. Think ReLU, the rectified linear unit.
Right.
The theory confirms that for many standard setups, feed-forward networks, transformer blocks, the stable rank, is often bounded by a small numerical constant. And crucially, that bound is independent of how wide your network is.
So what is it about ReLU that does that?
Well, think about what it does. It forces half the values to zero, right? And because it's non-centered, meaning the average of the outputs isn't zero, it introduces a very predictable structure. This creates what the paper calls a large mean-induced rank 1 spike in the gram matrix of the features.
A rank 1 spike. So if you're trying to visualize that landscape, it means one direction is just overwhelmingly dominant, like the gravitational pull of a single massive planet.
That's a great way to put it. That one dominant spike in the spectrum essentially flattens everything else, suppressing the effective dimension and keeping that stable rank really small.
Yeah.
Theoretically, for ReLU, it's bounded by something like 2 pi plus some small error terms.
2 pi. That is a tiny number compared to a network with, say, 4,000.
Exactly. And that low stable rank is precisely why standard optimizers like Atom can struggle. Atom tries to scale down gradients in directions with high variance, but in this landscape, it gets trapped. It sees that one dominant spike, and it can't differentiate the useful signal from the noise in all the other directions.
But spectral methods are designed for this kind of space.
They're inherently designed for it. And we confirmed this empirically, right, in the NanoGPT-scale training experiment.
You did. What did you find?
We measured the stable rank of the features feeding into the internal MLP and attention blocks. And even though the architecture's dimension was in the thousands, the stable rank it stayed consistently low, often below 12.
So the theory holds up. Strong feature degeneracy is just a pervasive property inside these networks.
It is. The one exception, though, is the input embedding layer.
Right, where the raw data first hits the model.
It's different there because you're dealing with raw, sparse token data, not these dense processed activations. The stable rank of the raw token matrix turns out to be just the inverse of the frequency of the most common token.
Okay, so what does that work out to in practice?
In our tests, it was around 26, which is still low, but it's noticeably higher than the 12 we see deep inside the network. And that distinction, it turns out, is really critical for applying Muon correctly.
Okay, so we've established the features are squashed, low stab A. Now for the other side. How does the gradient find enough room to work with? We need that numerator, the nuclear rank MR G, to be large enough to get the advantage.
This is where the optimization dynamics get really fascinating. If you look at the gradient right at initialization, when the weights are all zero, its nuclear rank is actually small. Maybe around 1.
So at the very beginning, there's no spectral advantage. Muon and Atom are on a level playing field.
Correct. But then watch what happens after just one single gradient descent step. That single step drastically changes the next gradient. The new gradient gets multiplied by this complex matrix polynomial. Let's call it t theta.
T theta. Okay, that sounds pretty dense. Is there an analogy for what that matrix is actually doing?
There is. Think of it like a spectrum leveler or a sound equalizer. Remember that one huge rank 1 spike dominating the feature space?
The massive planet, yeah.
The first optimization step is driven almost entirely by that one direction. T theta uses the information from that first step to actively dampen or squash down that dominant direction.
I see. So by dampening the loudest frequency, you can suddenly hear all the other quieter ones.
That's the perfect analogy. It flattens the spectrum, making all those smaller, previously hidden dimensions suddenly accessible to the gradient. And the immediate result is that the nuclear rank of the new gradient jumps dramatically and starts scaling linearly with the network dimension.
So the optimization process itself, after just a tiny bit of exploration, creates the very condition that spectral methods need to thrive.
It's a completely emergent property. And the analysis shows this isn't just a brief flash. That low nuclear rank at the start is purely temporary. After a short burn-in period, maybe a few hundred steps, the nuclear rank scales up to be proportional to the network dimension.
And it stays there. This advantage isn't momentary.
No, it persists. It holds for a window of iterations that represents a really significant fraction of the total training time you'd need to hit your target accuracy. And again, the empirical data from NanoGPT confirms this perfectly.
The internal transformer blocks.
The MLPs, the attention layers, their nuclear ranks were consistently large. I mean, reaching into the hundreds and just staying there for the bulk of the training run. The model really holds up.
Which brings us to the synthesis. How do we apply this layer-by-layer condition to a full transformer?
Well, we use a more generalized model, which basically confirms that for any complex block, the condition for spectral superiority still comes down to the stable rank of the core activation feeding into it. The degeneracy of the feature matrix is always the primary filter.
So if we look at a standard transformer, the internal weights for attention and the MLP.
Right, the WQ, WK, WV, WO for attention, and the MLP weights. They all interact with these highly processed post-activation hidden states.
The exact same states we just showed have that incredibly low, numerically bounded stable rank.
Precisely. And since we also just showed that those same layers develop these high-gradient nuclear ranks during training, the condition in R of G is greater than S of A is just. It's strongly satisfied for almost every internal block.
That is the geometric justification for using Muon in the middle of the network.
It is. And now contrast that again with the boundary layers, the input embedding and the LM head.
We already said the embedding layers features have a stable rank that's only moderately low. It's not bounded by 2 pi.
Right. So the resulting ratio, that advantage ratio of nuclear rank over stable rank, it's just not as overwhelmingly large for the embedding layer. The predicted spectral advantage is much milder.
Which explains a common practice I've seen, where engineers will apply Muon to the internal blocks, but keep the embedding and LM heads on a standard Atom W update.
It explains exactly why that architectural separation works. This research gives you the why.
Okay, so this all makes it sound like spectral optimization is just perfectly tailor-made for modern networks. But you have to stress, it's not a cure-all.
No, absolutely not.
Let's talk about the cautionary tale. If you change the geometry, that spectral advantage can completely evaporate.
This is the vital counterbalance. The success is conditional on the features being degenerate. We ran a synthetic regression experiment, and we just swapped out RAOL-U for the SWIGGL-U gated activation.
SWIGGL-U, and what's different about that?
SWIGGL-U is smoother, and it's self-gated, so it tends to produce more nearly centered post-activations, and that's the key. Centering the features suppresses that mean-induced rank 1 spike we talked about.
Ah, so without the single dominant planet.
The feature spectrum spreads out much more evenly, and that means the stable rank is no longer capped by a tiny constant like 2 pi.
It starts to grow with the network dimension instead.
It goes proportionally, so now suddenly your denominator is rising quickly. When we chart the optimization, the nuclear rank or numerator, which scales with dimension, it suddenly dips below the rising stable rank line. The condition is violated.
And the practical consequence, what happened to performance?
In this high stable rank, non-degenerate landscape, standard Euclidean gradient descent just, it significantly outperformed spectral gradient descent. It reached a better minimum, and it did it in far fewer iterations.
So that experiment proves it. The feature degeneracy is an absolutely necessary precondition.
It's a must-have.
So what does all this mean for you, the listener, the one actually running the training job?
Well, the success of an optimizer like Muon isn't some black box magic. It's not about some clever adaptive scaling.
No, it's a direct result of mathematically recognizing the intrinsic spectral properties of the system you're training. Spectral methods are perfectly adapted to exploit this ill-conditioned regime where your features are squashed, but your gradient is still trying to explore this vast space.
This research really identifies these two metrics, the nuclear rank of the gradient and the stable rank of the features, as the true determinants of your optimization efficiency.
It suggests the search for the best optimizer is really a search for the best geometry to match the layers you're updating. And that leaves us with a really fascinating provocative thought. If the choice of your activation function, like a ReLU, is what's fundamentally dictating this feature geometry, creating the degeneracy that spectral methods exploit, what if we could engineer future activation functions, perhaps ones that create even more complex non-Euclidean feature geometries? What other unknown specialized optimization geometries might be out there just waiting to be discovered that could perfectly match those new structures? The future of fast training may lie entirely in tailoring the optimizer to the layer's spectral shape.